When you imagine the solar system, chances are you're not thinking of the real thing. You're probably thinking of diagrams, the neat orbits, the textbook illustrations, maybe a model from school where each planet is a painted ball on a wire. But the truth is, none of those get it right. The actual solar system is far stranger, far more detailed, and far more beautiful than any drawing can capture. And the only way we know that is because we've seen it. We've sent cameras to places we'll never walk, pointed telescopes where our eyes can't reach, and collected pictures that rewrote our understanding of what's out there. Some of these images look ordinary until you realize what they're showing. A pixel that holds our entire planet. A plume of water shooting into space from a tiny moon. Storms larger than Earth raging on worlds so far away they look like dots to the naked eye. Others are breathtaking the moment you see them, like Saturn's rings in crisp detail or the first true landscape from the surface of Mars. Together, they form a kind of photo album of the solar system, except this isn't a collection of memories. It's evidence. Every frame is a discovery, every photograph a turning point. That's what makes this journey through images so different. It isn't about art and it isn't about imagination. It's about seeing the solar system as it really is, messy, alien, alive, and letting the pictures speak for themselves. Because once you've seen these worlds with your own eyes, even through the lens of a spacecraft, it's impossible to think of them as abstract. They stop being ideas and start being places. And once that happens, you can't go back to thinking of the solar system the way you did before. When people think of space photography, the mind usually jumps straight to colorful nebulae or detailed close-ups of planets, but the earliest space images were nothing like that. They were black and white, grainy, and often looked like someone had pointed an old television camera at static. Yet those were the shots that kicked everything off. Because for the first time in history, humanity wasn't guessing what things looked like from above. We were actually looking. That shift mattered more than the image quality. Take the case of Earth. Before 1946, nobody had ever seen the Earth from beyond the thin upper atmosphere. That year, a captured German V-2 rocket, launched from White Sands, carried a camera up to about 105 kilometers and snapped the first photographs of Earth's curvature. The pictures were primitive, yes, but they proved what people had only imagined. Our world has edges, arcs, a visible horizon that bends away. These low-resolution frames, recovered from film strips after the rocket's parachute descent, captured the dark void of space against the planet's hazy limb, a stark, visual proof of our world's roundness. You don't get that from standing on the ground, or even from an airplane. You needed to leave Earth. Those blurred black and white frames look almost like medical x-rays of the planet, but they were enough to confirm that a new era had begun. Fast forward 2 decades and you get one of the most famous images ever taken. Earthrise, captured during Apollo 8 in 1968. On December 24th, the astronauts weren't even scheduled to photograph that scene. They were orbiting the moon, conducting tests, when Bill Anders spotted Earth peeking over the lunar horizon from about 93,000 miles away. He quickly grabbed a Hasselblad 500 EL camera loaded with color Ektachrome film and took the shot. The photo shows our planet rising above the stark, dead gray of the moon's surface, hanging there like a fragile ornament in a black void. Scientists learned little new from that picture in terms of geology or physics, but society learned everything. It landed on magazine covers, posters, and eventually textbooks. It gave environmental movements a rallying symbol. You can analyze it technically, film type, exposure, distance, but what made it powerful was that it made billions of people stop and realize, that's us, all of us, on one tiny world. Its cultural ripple even influenced the first Earth Day in 1970, underscoring humanity's shared vulnerability in the cosmos. For the first time, we saw ourselves not as citizens of nations, but as passengers on the same delicate sphere, drifting through infinite darkness. That revelation transcended science. It awakened perspective, humility, and a collective sense of stewardship that no experiment or equation ever could. Then came the blue marble in 1972, snapped by the Apollo 17 crew on their way to the moon. Unlike Earthrise, which shows a half-lit world, this one captured Earth fully illuminated, with Africa and Antarctica in crisp view from roughly 29,400 kilometers out, thanks to the mission's unique southward trajectory over the Indian Ocean. If Earthrise gave us perspective, Blue Marble gave us completeness. It's often said this is the most reproduced photograph in history, and it's easy to see why. For once, there was no artistic guesswork, no map projection, just Earth as it is. Clouds spiraling, oceans glowing deep blue, land masses drawn in real colors. This wasn't a scientist's diagram, it was reality. Of course, not every famous image looks beautiful in a conventional sense. Take the pale blue dot, taken by Voyager 1 in 1990. By then, Voyager had already completed its planetary tour and was drifting out toward interstellar space. Mission engineers decided to turn its cameras back toward the solar system one last time at the urging of astronomer Carl Sagan. Earth showed up as a tiny pinprick, barely a pixel across, sitting in a beam of scattered sunlight. If you didn't know what you were looking at, you'd miss it. And yet, that's the point. That dot is Earth. That dot is every person, every story, every memory. The raw data was minimal. No new science, no hidden detail. But the impact was enormous. That single pixel forced people to think about scale. Think about how we view ourselves in a universe that doesn't even notice us. Sagan himself reflected on it in his 1994 book, Pale Blue Dot, calling it a reminder to preserve and cherish the pale blue dot, the only home we've ever known. So, why start with these pictures? Because they set the tone for everything else the solar system would reveal. The early shots told us something simple but profound. Images aren't just data, they're context. They reframe questions we didn't even know we had. How small are we, really? How fragile is the atmosphere? What does our planet look like when you strip away the myths and just take a photograph? These are questions the first space images forced us to ask, and every mission since then has been answering in new ways. If you were an astronomer in the early 20th century, Mars was mostly guesswork. Through Earth's telescopes, it looked like a reddish disk, sometimes showing dark smudges and bright caps that people interpreted as continents and polar ice. Popularized by Percival Lowell's observations from the 1890s through the 1910s at his Arizona observatory, that's where the canal theories came from. Straight lines that some thought were irrigation networks built by intelligent life. In truth, those were optical illusions, artifacts of low resolution known as gemination, where faint features doubled due to Earth's atmospheric turbulence and observer bias. The real Mars stayed hidden until we sent cameras close enough to peel back the mystery. Mariner 4 was the first to do it in 1965, flying past the planet and snapping 22 photos from about 9,700 kilometers away. They weren't pretty, cratered, desert-like, and nothing like the lush landscapes people imagined. For many, it was disappointing. But in hindsight, those images were historic. They killed the last serious holdouts of the canal idea. More importantly, they revealed that Mars had been geologically active in the past, because you don't get impact craters unless you have a solid surface. A blurry dot had become a world with texture. Fast forward a decade to the Viking orbiters and landers in the 1970s, and suddenly the picture sharpened. The orbiters sent back panoramas of huge volcanoes like Olympus Mons, canyons like Valles Marineris, and floodplains carved by ancient water. The landers gave us surface shots of a rusty, barren desert under a pinkish sky. For the first time, we weren't seeing Mars as theory or sketch. We were standing on it, at least through the lens of a camera. These images taught scientists that Mars had once been wetter and more dynamic than it is now. And then the modern era arrived. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have turned Mars from a place we could only imagine into a place we can almost walk through. You've probably seen the panoramas, 360-degree views where you can spin around and feel like you're standing in Jezero Crater or Gale Crater. But here's the part that often gets overlooked. The detail in these images isn't just for show. For scientists, every pixel can reveal mineral content, grain size, and signs of past water. A single close-up of a layered rock tells you about sediment deposition billions of years ago. Take Perseverance. In 2024 and 2025, it captured visible light auroras on Mars for the first time. Think about that. An aurora, something we associate with Earth's poles, glowing in the thin Martian atmosphere. The rover's cameras picked up green light emissions from oxygen molecules high above. To the human eye, standing there, it would have looked like a faint glow over a barren landscape. That kind of image doesn't just add beauty, it tells us Mars has atmospheric processes we didn't fully appreciate, and that even a planet with patchy magnetism can still produce auroras from solar protons exciting the exosphere. Perseverance also kept running into dust devils. The cameras caught spiraling columns sweeping across Jezero crater, sometimes towering over 2 kilometers high. They're not just a curiosity. By analyzing the way dust devils look in motion sequences, scientists can calculate wind speeds, study how dust interacts with the atmosphere, and understand climate dynamics. On Earth, you can walk away from a dust devil. On Mars, they reshape how instruments function and even how solar-powered rovers survive. So, those cool clips are more than postcards. They're atmospheric science in action. And of course, there are the landscapes that almost feel familiar. High-definition shots from Curiosity show dried riverbeds with rounded pebbles, the kind you'd find in a stream on Earth. Perseverance's Mastcam Z has sent back color images of layered cliffs that look like the Grand Canyon in miniature. These aren't exaggerations, they're literal records of ancient environments. To look at those photos is to look back billions of years and see evidence of lakes, streams, and maybe conditions that could have supported life. Here's the thing. Every stage of Mars imaging rewrote the story. First, it was a blurry red dot. Then, a cratered desert. Then, a world with volcanoes, valleys, and the scars of flowing water. And now, through rover eyes, it's a place that feels tangible. Like you could lace up your boots and start hiking. The transformation is not about making Mars prettier, it's about making it real. Every rover photo, every panorama, every close-up of a dust-covered rock is a reminder. This isn't science fiction anymore. Mars is a physical place with a history, and the images prove it. When we first looked at Jupiter through telescopes, what stood out were the stripes and the great red spot. Those bands of color seemed permanent, and the spot was this mysterious storm that had been raging for centuries. First reliably observed in 1831, though hinted at earlier by Robert Hooke in 1664. But no one really knew what those features looked like up close. They were blurry even in the largest observatories. That changed in 1979, when Voyager 1 and Voyager 2 flew past the giant planet. Suddenly, Jupiter wasn't just a painted ball in textbooks. It became a dynamic, violent world with details no one could have predicted. The Voyager images of Jupiter's atmosphere shocked scientists. Instead of smooth stripes, they revealed turbulence. There were swirls, eddies, chaotic cloud systems where ammonia and water clouds interacted in ways we'd never modeled. The Great Red Spot itself turned out not to be a flat disk, but a massive cyclone with depth and complex color gradations, with smaller storms surrounding it like satellites orbiting a planet. In some frames, you could actually see how storms interacted, merging or shredding apart, which changed the way meteorologists thought about planetary weather systems. But the real surprises came not from Jupiter itself, but from its moons. Io, for example, looked at first like a pizza covered in sulfur and lava deposits. But when Voyager imaged it more closely, scientists realized they were witnessing something no one expected: active volcanism. Plumes were rising hundreds of kilometers into space, captured in images as faint arcs above the limb of the moon. These weren't frozen relics of ancient geology. They were happening in real time. It was the first time anyone had ever seen active volcanoes beyond Earth. And this discovery reshaped the way we think about tidal heating. The images showed that the gravitational tug-of-war between Jupiter and the other Galilean moons was literally kneading Io's interior, keeping it molten. Europa's images were just as groundbreaking, but in a subtler way. Voyager showed a smooth, bright surface etched with cracks and streaks, almost like someone had taken a sharp tool and scratched across a sheet of ice. Unlike heavily cratered moons, Europa didn't show much evidence of impacts. That meant its surface was young, geologically speaking. Scientists realized those fractures could be from an ocean underneath, shifting the ice above. One picture of a cracked ice field was enough to trigger decades of speculation about subsurface oceans and possible habitats for life. Even now, those first images are still used in presentations about astrobiology because they sparked an entirely new line of thinking. That life could exist in hidden oceans beneath ice, warmed not by sunlight but by tidal forces. Then there was Ganymede, which Voyager revealed as not just another cratered rock, but a world with grooves and ridges hinting at tectonic processes. At the time, this suggested internal activity that nobody had accounted for. Callisto, by contrast, looked ancient, its heavily cratered surface preserved like a fossil. Putting the images of all 4 moons side by side showed that even within one planetary system, diversity was extreme. It was like finding 4 different planets orbiting a single giant. Fast forward to more recent years, and missions like Juno have pushed this imagery even further. Juno's close passes, starting in 2016 and continuing through 2025, have given us some of the highest resolution pictures of Jupiter's cloud tops. These images show storms in intricate detail, cyclones arranged in geometric patterns at the poles, turbulent eddies that look like oil paint swirling on water. They aren't just pretty. Each photo is a data set. The color variations reveal chemical differences, the textures reveal motion, and the shadows reveal height differences in the atmosphere. When Juno's camera caught the polar cyclones, each as large as Earth, arranged in near-perfect polygons, it raised questions about atmospheric stability that scientists are still working to answer. Juno also turned its cameras toward Io and captured active eruptions, confirming that Voyager hadn't just caught a lucky snapshot decades ago. Io is still erupting, still reshaping itself continuously. The before and after imagery shows new deposits and altered terrain, proving that the solar system isn't static. It's changing on human timescales, even if slowly. Every new frame adds to a timeline of planetary activity that helps scientists build models of how moons evolve. The thing about Jupiter and its moons is that their images didn't just satisfy curiosity, they redefined planetary science. Before Voyager, moons were considered frozen, inactive leftovers. After Voyager and now Juno, moons are seen as diverse, complex worlds. Some volcanic, some hiding oceans, some scarred by ancient history. That all came from pictures. And it's a reminder that each frame of a planet or moon isn't just a photograph. It's evidence. It's data encoded in light. It's proof that our solar system is stranger than we thought, and that we can only understand it by looking closely. If Jupiter's moons forced scientists to rethink what a moon could be, Saturn's system did the same thing for rings and small worlds. Before spacecraft reached it, Saturn was mostly a telescope curiosity. Astronomers saw the rings, sure, but they looked like a flat, static structure, like grooves on a record. Nobody really knew how dynamic they were. That changed when spacecraft actually flew past. Pioneer 2 in 1979 and Voyager 1 and 2 in 1980 gave us the first hints, revealing ring spokes, kinks, and density waves. But it was Cassini that transformed our understanding completely. The first high-resolution images from Cassini in 2004 pulled the curtain back. Suddenly, the rings weren't smooth. They were full of gaps, waves, braided patterns, and clumps that shifted in real time. The photographs revealed that each ring was made up of countless particles, everything from dust-sized grains to boulders, colliding and rearranging under the pull of Saturn's gravity and the tug of nearby moons. Those pictures weren't just beautiful. They told us the rings are alive, in motion, constantly sculpted by physics. When Cassini took close-ups that showed individual ringlets splitting and reconnecting, it forced scientists to start treating the rings as a kind of laboratory for orbital mechanics. But it wasn't only the rings. Saturn's moons started stealing the show. Enceladus was the biggest surprise. Cassini's cameras picked up faint plumes shooting out from the South Pole, jets of water vapor laced with organic molecules. At first it was debated. Were those real geysers or imaging artifacts? Multiple passes confirmed it. The images showed plumes stretching hundreds of kilometers into space. Later analysis revealed that the material came from a subsurface ocean beneath the ice crust. Suddenly, a small icy moon became one of the most likely places to host life in the solar system. The photos were the key. Without them, no one would have believed such a tiny moon could harbor something so dramatic. Titan was another revelation. Early images showed a thick orange haze that blocked the surface. It looked like a fuzzy ball, but Cassini's radar instruments combined with its imaging systems pierced through the atmosphere. Pictures revealed lakes and seas of liquid methane and ethane, rivers carved into the landscape, and even dunes stretching for hundreds of kilometers. In many ways, Titan looked like Earth, only with hydrocarbons playing the role of water. The Huygens lander's descent images in 2005 were especially striking. They showed channels, rocks, and a horizon under a thick sky. It was the first and only time we've seen the surface of Titan directly, and those frames proved it's a world with complex weather and geology. The images of Saturn itself also changed how we think of giant planets. Cassini documented storms that dwarfed Earth, like the hexagon at the North Pole. That six-sided jet stream, first hinted at in Voyager pictures, became a focus when Cassini sent back crystal-clear views of its structure. High-resolution shots showed it wasn't a temporary weather pattern, but a stable feature, persisting for decades. Capturing it over time gave scientists data to test fluid dynamics on a planetary scale. And then there were the storm systems, great white spots that erupted and spread across the planet, imaged in progress rather than only after the fact. Even the end of Cassini's mission added to the imagery legacy. In 2017, during its grand finale, the spacecraft dove between Saturn and the inner rings. It sent back close-ups of the ring particles and the upper atmosphere, showing details nobody had ever expected to see. Those final frames were the closest look we've ever had at the ring-planet boundary, and they revealed a region rich in fine structure, not empty space as once assumed. Since Cassini, telescopes like JWST have picked up where it left off. In 2023, Webb imaged Enceladus's plume stretching nearly 10,000 kilometers, 20 times the size of the moon itself. Capturing that scale was only possible with the new infrared sensitivity. Those images don't just look spectacular. They confirm that the subsurface ocean is venting continuously into space, creating a natural sample return mission. So, when you look at pictures of Saturn, you're not just looking at a planet with pretty rings. You're looking at a system where every image revealed another surprise. Rings that act like living structures. A moon that spews ocean water into space. Another moon with lakes and rivers of methane, and atmospheric patterns that challenge our theories of weather. The cameras turned Saturn from a symbol of beauty into a place of discovery. Each picture is both evidence and invitation, proof that the outer solar system is far stranger and far more active than anyone guessed. If Mars showed us landscapes that felt familiar, Venus taught us a different lesson. Sometimes to see a planet, you can't rely on normal photography at all. From Earth, Venus has always been the morning star or evening star, dazzlingly bright but frustratingly opaque. Its thick carbon dioxide atmosphere, shrouded in sulfuric acid clouds, hides the surface completely. Through a telescope, it looks like a smooth white ball. No detail, no mountains, no valleys. For centuries, people imagined what lay beneath. Swamps, oceans, jungles, deserts, but nobody could prove anything. The only way forward was to invent a new way of seeing. The first spacecraft to reach Venus in the 1960s, the Soviet Venera series, gave us hints. Some of the landers survived long enough to send back black and white images of the surface. First from Venera 9 and 10 in 1975, with color panoramas added by Venera 13 and 14 in 1982. The pictures were grainy but undeniable. Flat rocky plains, scattered stones, and a hazy horizon under an orange sky. Just a handful of frames were enough to confirm Venus wasn't a swamp, it was a furnace. Temperatures over 450 degrees Celsius, pressures strong enough to crush submarines, and clouds that blocked all sunlight. Those early images were more about endurance than clarity, but they set the stage. They proved you could land and look, if only for a few minutes before the environment destroyed the probe. The real breakthrough came with Magellan in 1990. Instead of taking photos in visible light, Magellan used radar to map the entire planet. It sent radio waves through the clouds and measured the echoes to build detailed images of the terrain. Suddenly, Venus went from a blank sphere to a world full of mountains, plains, ridges, and massive volcanoes. The images were striking, false-colored maps showing features thousands of kilometers wide. You could see huge volcanic structures like Mont Mons, lava channels longer than the Nile River, and vast highland plateaus. For geologists, this was a gold mine. For the first time, they could compare Venus's surface processes with Earth's. One of the most important things those radar images revealed was how young the surface looked. Unlike the Moon or Mars, Venus didn't have a landscape dominated by craters. Instead, the craters were sparse and scattered, suggesting the surface had been resurfaced by volcanic activity within the last few 100 million years. That meant Venus wasn't geologically dead. It was active, or at least recently active, and radar images even showed features that looked like collapsed lava domes and fractured plains, hinting at tectonic activity, though not plate tectonics like Earth. In 2023, scientists went back to Magellan's old data with new techniques and found something even more dramatic. By comparing radar images taken months apart in the early 1990s, they spotted changes in volcanic vents. One vent near Mont Mons doubled in size, with a new outflow consistent with fresh lava. It was the first direct evidence of ongoing volcanic eruptions on Venus. What's remarkable is that this discovery didn't come from a new spacecraft. It came from squeezing more insight out of decades-old images. That shows how powerful imagery can be, even long after a mission ends. The Japanese spacecraft Akatsuki added another dimension. Launched in 2010 and orbiting Venus until 2025, it gave us long-term monitoring of the atmosphere. Its ultraviolet and infrared cameras captured cloud structures in incredible detail. Giant waves rolling across the planet, super-rotating winds whipping around the equator in just 4 days, and strange stationary waves that stretched thousands of kilometers. These weren't surface images, but they revealed how the atmosphere behaves, something that's impossible to see from Earth. When you look at those false-color UV images, the contrasts aren't just pretty, they map real chemistry and motion in the clouds. Venus taught scientists to be flexible. With most planets, you point a camera and take a picture. With Venus, you use radar, ultraviolet, infrared, and whatever else works, because visible light won't get you anywhere. Each type of image is like peeling a different layer. Radar for the surface, infrared for the lower atmosphere, ultraviolet for the cloud tops. And together, they give you a composite picture of a world that is as extreme as it is fascinating. What stands out most is how deceptive Venus is. From a distance, it looks calm, almost featureless, like a serene pearl in the sky. But the images from Venera, Magellan, and Akatsuki reveal a planet of violent heat, crushing air, volcanoes, and a storm system that never rests. Every picture, whether a black and white frame from a dying lander or a radar map spanning half a hemisphere, chips away at the mystery. And they all remind us that beauty and danger can exist in the same place. For most planets, we have a steady stream of images across decades. Mars has landers and rovers, Jupiter has Juno, Saturn had Cassini, but Uranus and Neptune sit at the edge of what our spacecraft have touched. And for both, almost all of what we know still comes from a single mission, Voyager 2. It flew past Uranus in 1986, at a closest approach of about 81,500 kilometers, and Neptune in 1989, at roughly 4.4 million kilometers, taking the only close-up pictures we've ever captured. That means every time you see a detailed image of either of these ice giants, you're mostly looking at snapshots taken more than 30 years ago. And yet those images completely changed how we see them. Before Voyager, Uranus was barely more than a cyan disk in telescopes. It seemed bland, even featureless. Voyager's images confirmed its pale blue-green color, the result of methane in the atmosphere absorbing red light, but they also showed faint cloud bands and a strangely tilted magnetic field. The most surprising discovery came not from the planet itself, but from its moons. Voyager revealed Miranda, a small moon with a jumbled surface that looked like it had been smashed apart and reassembled. The images showed cliffs taller than Mount Everest and patchwork terrains that didn't fit any single geologic process. Just a handful of close-up shots forced scientists to admit Uranus's moons were stranger than anyone expected. Neptune's encounter was even more dramatic. Through Voyager's camera, Neptune transformed from a fuzzy point of light into a deep blue world, with a massive storm system, the Great Dark Spot. It looked almost like Jupiter's Great Red Spot, a vast cyclone wider than Earth, caught in a planet with the fastest winds in the solar system. The images also showed high, bright clouds casting shadows, proving Neptune's atmosphere wasn't just a static blanket of gas, but a dynamic, storm-driven system. And then there was Triton, Neptune's largest moon. Voyager's pictures revealed active geysers, spouting nitrogen into the thin atmosphere. Dark streaks painting the icy surface, and landscapes shaped by processes no one had seen before on any moon. That single flyby showed Neptune wasn't an afterthought. It was a world of extremes. For decades, those Voyager frames were all we had. But recently, new tools have brought Uranus and Neptune back into focus. The James Webb Space Telescope has taken infrared portraits that finally show details missed by Voyager. In 2023, Webb imaged Uranus with an unprecedented view of its rings, including faint outer ones invisible before, and a glowing polar cap that hints at strange seasonal changes. The same telescope turned its eye on Neptune, revealing crisp views of its rings and high-altitude methane clouds. These aren't artist impressions. They're real images captured in wavelengths our eyes can't see, processed to show features Voyager's cameras couldn't. More recently, in August 2025, JWST announced the discovery of a new tiny moon orbiting Uranus, bringing the total to 29, and highlighting ongoing spectral studies of faint rings and inner moons for both planets. They prove these planets are still active, still surprising, even if no spacecraft has visited in decades. And that's the frustration. The best images of Uranus and Neptune are still rare, and they leave more questions than answers. Why does Neptune have storms that appear and vanish within years, unlike Jupiter's centuries-old Great Red Spot? Why does Uranus radiate less heat than expected, even though its interior should still be warm? The images hint at answers, but don't explain them fully. Every time scientists revisit the Voyager data, or get a fresh Webb snapshot, the story expands, but not enough. So the pictures of Uranus and Neptune sit in a strange category. They're some of the most beautiful and haunting in planetary science, but they're incomplete. They show us just enough to prove these are dynamic worlds, not frozen backwaters. But they also remind us of how little we've seen. The images force a simple question. Why haven't we gone back? Every other giant planet has been revisited, studied in detail, and mapped thoroughly. These two remain in many ways the forgotten giants, defined by a single flyby and a handful of telescope views. And yet each image we have suggests they might hold some of the biggest surprises left in the solar system. Before 2015, everything we knew about Pluto came from Earth-based telescopes. The images were vague, just a shifting blur of brightness as the dwarf planet rotated. At best, we could detect changes in surface reflectivity and color, which hinted at regions with ice or darker compounds like methane and tholins. But we couldn't see any details. It was like trying to understand the surface of the moon by staring at a street lamp through a foggy window. That's why the New Horizons mission mattered so much. It wasn't just a flyby, it was the moment a distant concept turned into a real place. When New Horizons finally reached Pluto in July 2015, with closest approach on July 14th at about 12,500 kilometers, it didn't just send back better pictures. It delivered a complete transformation. The very first high-resolution images showed a world more complex than anyone had imagined. Right away, people saw that now iconic heart-shaped feature, Tombor Regio. It looked almost cartoonish, like something drawn for clarity, not reality, but it was real. And more than that, it was geologically diverse. One lobe of the heart, called Sputnik Planitia, turned out to be a massive basin filled with nitrogen ice. The surface wasn't smooth. It had strange polygonal patterns, like cracked pavement or frozen mud, but on a scale of tens of kilometers. These weren't random. They were convection cells, slowly churning over millions of years as the nitrogen ice rose and sank. In the images, you can see those cellular structures, rimmed with ridges and separated by troughs. Just by looking, you'd think it was a frozen pond. But this pond is hundreds of kilometers across and powered by internal heat from beneath Pluto's crust. That one image alone told scientists that Pluto wasn't frozen solid. It had an energy source inside, something capable of keeping this surface mobile. Other areas showed towering water ice mountains, some reaching 3 to 4 kilometers high, jutting out of the plains like isolated peaks. One in particular, Right Mons, appeared to have a central depression and signs of ancient cryovolcanism. Not lava, ice, ammonia, and maybe even liquid water erupting through the surface. And the images weren't blurry approximations. They were detailed enough to trace slopes, spot boulders, and examine the texture of ridges. What made Pluto even stranger were the haze layers. As New Horizons flew past and looked back toward the sun, it captured a series of images that revealed over a dozen distinct layers of atmospheric haze, stacked like sheets of frosted glass. This was unexpected. Pluto's atmosphere was supposed to be thin and cold, barely held by its gravity. Yet these pictures showed that it was structured, layered, and full of active processes. Some of the haze particles may have formed high in the atmosphere from sunlight breaking apart methane and then settled slowly, scattering light along the way. In the images, you can see the way the light bends through these hazes. It makes Pluto look like a small, distant version of Earth at sunset, glowing, fragile, and alive in its own quiet way. Then came Charon, Pluto's largest moon. Before the flyby, all we had was a barely resolved blob. But New Horizons' close-up images revealed a battered surface of canyons, troughs, and a massive equatorial fracture system that suggested internal expansion. It looked like Charon had once been geologically active. There were strange surface features that didn't match any known types: giant chasms, ridged plains, and dark patches of what might be tholins, organic molecules formed from radiation hitting methane. Again, these were things you couldn't even guess from telescopic views. They only appeared once you had a camera close enough. But New Horizons didn't stop with Pluto. After the flyby, it continued deeper into the Kuiper belt, a vast donut-shaped disk of icy bodies beyond Neptune's orbit, stretching from about 30 to 55 astronomical units and serving as the solar system's third zone of primordial remnants. And in 2019 visited Arakoth, a contact binary object made of two lobes gently fused together. The images showed a red, primitive surface, with few craters and smooth contours, suggesting it had been untouched since the early solar system, a pristine protoplanetary disk relic. Unlike the active geology of Pluto, Arakoth was more like a time capsule. The pictures gave planetary scientists a direct look at how objects might have formed in the earliest days of the solar system, before planets even existed. Ongoing New Horizons analysis, including a 2025 geologic map, continues to reveal its layered structure from gentle mergers. The Kuiper belt itself, home to Pluto and other dwarf planets like Haumea, Makemake, Quaoar, and Orcus, as well as short-period comets, remains largely unexplored. But recent discoveries have deepened its mysteries. In March 2025, Hubble identified a potential triple Kuiper belt object system, the second known, supporting theories of gravitational collapse formation for these icy planetesimals. A September 2025 orbital analysis of extreme trans-Neptunian objects hinted at an unseen Planet 9 shepherding the belt's structure. And earlier Subaru telescope surveys have uncovered new clusters of distant objects, suggesting dynamic sculpting by unseen forces. Now, nearly a decade later, scientists are still analyzing those images. Recent research in 2025 suggests Pluto's atmosphere might be collapsing as it moves away from the Sun in its elliptical orbit. This conclusion was made possible by revisiting the haze images and combining them with more recent occultation data. So even though the spacecraft took those pictures years ago, their scientific value continues to grow. There's also the emotional side of it. When people saw Pluto for the first time, really saw it, there was a collective reaction that caught even NASA by surprise. The images weren't just data, they were art. They showed a place that had been a pixel for decades, a ghost at the edge of the map, and turned it into a world. You could see the light falling on its surface. You could imagine what it would feel like to stand there under a dim sun with a pink sky glowing faintly above. That kind of reaction doesn't come from numbers, it comes from pictures. When we talk about images of the solar system, most people picture planets, moons, maybe an asteroid or two. But at the center of it all is the Sun, often left out of the conversation, not because it's unimportant, but because it's hard to look at. The Sun is too bright, too hot, and too dangerous to observe directly without specialized tools. Its visible light overwhelms surface details, requiring UV or radio wavelengths to probe the corona's multi-million-degree temperatures. For a long time, even professional telescopes avoided staring at it for too long. It was easier to study how it affected other things, solar flares disrupting satellites, solar wind shaping comet tails, than to photograph it in detail. But that changed. In the past 2 decades, we've built instruments tough enough and clever enough to do the unthinkable. Take close-up pictures of the Sun itself. And those images are nothing like what people expected. Let's start with SOHO, the Solar and Heliospheric Observatory, which launched in 1995 and began sending back full-time views of the Sun. It gave us our first long-term image library. Sunspots rotating across the surface, massive eruptions called coronal mass ejections blasting plasma into space, and loops of glowing gas rising and falling. These were time-lapse images at first, then high-resolution sequences that helped scientists track the solar cycle and predict space weather. They were useful, but they still kept a respectful distance. The Sun was a target, not a place. Then came SDO, the Solar Dynamics Observatory, in 2010. Its images were different. Suddenly we weren't just seeing the Sun as a glowing disk, we were seeing layers. SDO's ultraviolet cameras captured the Sun in multiple wavelengths, revealing different parts of its atmosphere: the chromosphere, the corona, the transition region. The images looked surreal. You'd see loops of plasma arcing over sunspots, shaped by invisible magnetic fields, glowing in oranges, purples, and greens depending on the wavelength. These weren't false colors for decoration. Each one represented real temperatures and elements: iron, helium, hydrogen, each glowing at its own frequency. The Sun stopped being a blur and became a textured, layered object, a place where motion never stopped. And then we went even closer. In 2018, NASA launched the Parker Solar Probe. Named after Eugene Parker and launched on August 12th, its goal wasn't just to image the Sun, but to dive into its atmosphere, to fly closer than any spacecraft ever had. Parker didn't have a traditional camera. It wasn't designed to take beauty shots, but it did have instruments that imaged the solar wind and corona in motion. The Whisper instrument, for instance, sent back pictures that looked like grainy clouds and beams, but to solar physicists, they were gold. They showed the fine structure of the corona, how particles accelerate, how waves ripple through the plasma, and how tiny jets and bursts feed the solar wind. In 2021, Parker flew through a coronal structure for the first time, what scientists call a pseudo-streamer. It's like flying into the engine of a storm and coming out with pictures of how the parts move. These weren't just diagnostic tools. They were raw views from inside the sun's influence, showing it not as a glowing sphere in the sky, but as an environment, a system you could actually fly through. At the same time, ESA's solar orbiter was providing another layer of images. Launched in 2020, it began imaging the sun's poles, areas we'd never seen up close before. The orbiter's cameras, particularly its Extreme Ultraviolet Imager, EUI, captured high-resolution shots of campfires, tiny bright spots that flicker across the surface. These weren't visible in previous missions. Each one might be a mini flare or a burst of magnetic energy. They're small, but they happen all the time, and they might be key to understanding why the corona, the outermost layer of the sun, is hotter than the surface itself. And here's the part that really forces you to rethink everything. Those close-up images show that the sun isn't a smooth ball of fire. It's not even made of flames. It's a seething, churning mass of plasma, twisted by magnetic fields and constantly erupting in unpredictable ways. Look closely at one of the high-res videos from Solar Orbiter, and you'll see loops and tendrils that resemble tangled ropes, some snapping, some tightening. These are not static objects. They rise, they collapse, they launch streams of matter into space. Every image is a moment in a continuous explosion that never ends. And they're not just visuals. The data from these images is helping engineers protect satellites, astronauts, and even power grids on Earth. Coronal mass ejections, solar flares, and sudden magnetic shifts can have ripple effects through our entire technological system. The better the images, the better we can model these events. Some missions even use AI to scan incoming imagery in real time and flag dangerous events. The pictures aren't just beautiful, they're part of our early warning system. But there's also something humbling about seeing the sun in this much detail. For all of human history, it's been our constant. It rises, it sets, it warms the Earth. But the close-up images show a different side. They reveal a star that's alive in the truest sense. Not with consciousness, but with motion, energy, unpredictability. It breathes radiation. It spits storms. It shapes the entire solar system with invisible forces. And the pictures prove it. Every frame taken by Parker or Solar Orbiter, every sequence from SDO shows us that the sun isn't just there. It's doing things all the time on every scale. From huge flares that stretch 1,000,000 kilometers to tiny flashes that last a second, it's all there in the images. You can't look at those shots and still think of the sun as a yellow circle in the sky. You start to see it for what it is. A vast, boiling engine, pulling all the strings, whether we notice or not. We've seen planets transform from smudges to landscapes, from theories to places. We've watched geysers on moons, storms on gas giants, and haze layers on distant dwarf planets. But for all the progress space imaging has made, we're still in the early stages of what it can do. Most of the solar system remains poorly photographed. Some worlds have only been visited once, some not at all. And the images we have, however breathtaking, are often just the first draft. The next generation of missions isn't just about looking again, it's about looking differently. Start with Europa Clipper. Launched on October 14, 2024, aboard a Falcon Heavy rocket, scheduled to arrive at Jupiter in April 2030, it's not just another flyby mission. It's designed specifically to image the surface of Europa in detail we've never had. Voyager and Galileo gave us glimpses, fractured ice, linear ridges, possible impact zones, but the resolution was limited and coverage was sparse. Europa Clipper will orbit Jupiter and make dozens of close passes over Europa, capturing high-resolution imagery using multiple instruments. We're talking about cameras that can pick out features a few meters wide. The goal isn't just to map the surface, but to find places where the ice is thin, fractured, or possibly venting material from the ocean below, supporting habitability assessments through plume spectroscopy for organics and salts. These future images won't be postcards. They'll be instructions. Engineers will use them to identify potential landing sites for future missions. Biologists will study them for chemical staining or discoloration that could suggest organic compounds. Geophysicists will model the surface stress patterns from the cracks and ridges to understand the tidal forces acting on the moon. A single image of a surface fracture might mean an ocean vent is active below. A dark patch might suggest exposed salts or frozen organics. And all of that comes from light captured at the right angle, at the right time, with the right sensor. Then there's Dragonfly, the mission set for Titan. Confirmed for a July 2028 launch on Falcon Heavy, with arrival in 2034. Instead of a rover, NASA is sending a drone, a rotorcraft that can fly from one site to another across the moon's surface. Titan is too cold for liquid water, but it has lakes of methane and ethane, rivers carved into the ice, and dunes stretching for kilometers. The drone will carry cameras that can image all of it from low altitude. Not a single view, but a moving sequence. Flyovers, close-ups, panoramas, descent footage. It's going to feel more like a documentary than a set of isolated frames. What's exciting about Dragonfly isn't just that it's going to take pictures, it's where it's going to take them. Titan's atmosphere is thick enough to scatter sunlight softly, which means surface lighting will be diffuse, like twilight on Earth. The drone's cameras will capture an alien world under a constant orange haze, flying over riverbeds and between ice formations that have never been seen up close. These won't be simulations. They'll be actual views from another world, recorded in motion, from just a few meters above the ground. And because Titan's gravity is low, the drone can travel far, making the photography more like exploration than surveillance. Meanwhile, ground-based telescopes are getting upgrades too. The James Webb Space Telescope has already taken infrared images of Neptune's rings and Uranus's polar cap that rival spacecraft views. But it's just the beginning. In the next decade, we'll see the rise of the ELT, the Extremely Large Telescope, in Chile, with first light expected around 2028 to 2030, and the Roman Space Telescope set for a May 2027 launch with its wide-field instrument for IR surveys, which will combine wide-field views with high sensitivity. Among the current crop of advanced observatories is the Vera C. Rubin Observatory, which achieved first light on June 23, 2025, and is now ramping up its legacy survey of space and time. With its 8.4-meter mirror and 3.2 gigapixel camera, it scans the entire visible sky every few nights, discovering thousands of new asteroids, Kuiper belt objects, and trans-Neptunian bodies each month. These instruments won't just image stars and galaxies. They'll track weather systems on gas giants, monitor activity on distant moons, and even capture asteroid flybys in more detail than current space-based missions, offering unprecedented tracking of solar system's small body populations, orbits, and potential hazards to deepen our understanding of planetary formation and dynamics. Another big shift is automation. Missions like Mars Sample Return will use autonomous landers and drones that can snap images and make decisions on the spot. The images won't just be sent back. They'll be interpreted in real time to guide robotic behavior. That means we're entering an era where images won't be for scientists alone. There'll be tools for machines, feeding navigation algorithms, geological analysis, and hazard avoidance. Photography becomes more than observation. It becomes interaction. And there are still gaps to fill. We've never had a dedicated Uranus or Neptune orbiter. No high-resolution maps of their moons, no repeat passes over the poles. Proposals exist, but funding and priorities always get in the way. Yet even one mission to either planet could explode our understanding. Think about it. Voyager 2 gave us nearly everything we know about those worlds in a few days of flybys. Imagine what an orbiter with modern cameras could do in 2 years. Looking forward, we're not just going to be taking more pictures. We're going to be taking different kinds of pictures. Multispectral images that reveal chemical composition, polarimetry images that expose texture, time-lapse sequences that show movement. The idea is to stop seeing these worlds as static and start watching them change, seasonally, geologically, atmospherically. And maybe the biggest leap will come from missions designed not by space agencies, but by private companies. SpaceX, Blue Origin, and others are building hardware that could one day send independent probes. If that happens, we might start seeing a shift in how space images are captured and shared. Not once every 10 years in a press release, but streamed, archived, and open for everyone. More eyes, more cameras, more perspectives. We've gotten used to seeing distant worlds in detail, but we shouldn't forget how recent that privilege is. Just 50 years ago, Pluto was a dot, Mars was a blur, Saturn's rings were visible but poorly understood. Now we have gigabytes of imagery showing valleys, dunes, geysers, and storms on worlds we can't yet reach in person. The future promises more of this, faster, in better quality, and with more context. The cameras are getting sharper, the missions are getting bolder, and the pictures we'll get in the next 2 decades might change everything we thought we knew.